Hello, everybody. We will start in a minute. Let me get things setting up. All right. So, hello, everyone. Welcome to another lecture on how things are made or how things are manufactured. So today we are going to talk about another manufacturing process. But first, we need to say, why do we need another manufacturing process? Because we have already learned about many ways to make things, right? Let's start with maybe this example. This coin maybe is a good example, and let's say how we can make a coin with the process that we've learned so far. But first, let's organize our thought and see what we have learned so far, or the process or the processes that we are familiar that maybe it's possible to make this coin. So we learn about machining, and we learn we can use either lathe or milling process, remove material, and get the desired shape that we want. We can automate this process using a CNC. Then later we learned that we can make things if the original material is in a form of sheet. Then we learned that we have two choices. If it is a metal sheet, then we can use the sheet metal working. And if it's plastic, then we have the choice of thermoforming. Right? And with the same things, with either metals or plastic, we learn another way to make things is by melting them. So we start by melting, and if the material is plastic, the process that we learned was injection molding. And if it's a metal, then we learned we have the option of casting. So, and with casting, we learned that we have three choices, and basically those are the mold. So we can have a mold made out of sand, or we can have a mold, which we call it a die or die casting, which made out of a metal. So die casting, or we can make the mold by using wax and ceramic. And later in previous lecture, we learned that if you are not happy with melting things, then maybe we can work with powder. So powder metallurgy was the other process that we learned, where we make a metals, we turn a metal to a powder, we compact it to the shape that we want, and then we sinter it, right? Looking at these tools that we have, and then this maybe simple part, a coin, if we try to make it maybe by machining, it's possible. We can program a CNC to machine a coin or a shape out of a metal and make a coin. However, it's going to be very expensive and long. Maybe just to get a $1 coin, it's going to cost us maybe $100. So it's not really plausible to do so. With plastic, of course, we don't want to make it out of plastic, but because it's a coin, and casting probably is not a very economical way to make coins because the process is slow and maybe it involves a lot of waste. And powder metallurgy, maybe we are not able to get the fine and detailed shape that we want. So as you can see, none of these processes are useful to make coins. Another good example that you may have seen, most likely, is the aluminum extrusion. So, which is a very useful part. Many frames for machines. We can use this. Many of you guys in your capstone project use, this is your good friend to make frames for, again, structures or machine. And they are lightweight and very strong, and mainly because of the cross section. But think of how these things can be made by the process that we've learned so far. So obviously, machining is not possible for making such a things. And maybe the closest things that we can think is casting, to cast something like that. However, this part that I have is short, but aluminum extrusion usually comes in 2 meters, 3 meters long. And now think about casting such a long part. It's almost impossible. And there are many other examples that we can think of. Let's say a screw or bolts like this one. So if I get my pen right, all right. So we may be able to make a thread by using a CNC machine or a simple lathe machine. Most likely you've done it. But if you're making only a couple of screws or bolts or nuts, that's a logical things to do. However, if you're making thousands and thousands of screws and bolts, then machining, it seems not to be a right way to do it. And if we look at like the ball bearings, just the ball itself, to make this nice sphere, of course, no CNC machine can do that. Maybe we can use powder metallurgy or maybe casting. However, the process is not fast enough to make or cheap enough to make thousands of, again, these balls in a short period of time. And think about these rings, the outer rings of the bearings with the shape that they have. So with powder metallurgy, you learned before, you prefer to make things that they have a smooth cross section or uniform cross section, so you can compact the powders. However, when the cross section for bearing has a hollow inside, maybe powder metallurgy is not a good way to make stuff. That's why we need to think of another manufacturing process. And this picture also, if you're not convinced by now that we need another manufacturing process, maybe this picture can convince you. This is a gigantic part. You can guess from this guy standing over here. So it's, I'm guessing probably it's about 2.5 meters in diameters. And maybe I'm guessing it's something around 4 meters in length. So this part, it's usually this gigantic part is used for big hammers in oil industry when they dig wells to get to the oil. So beside the application, but let's focus on how we can make these gigantic parts. So of course, with casting and all the things that you've learned about solidification, making such a big solid part maybe is not a wise thing to do. And this process, which today we're going to talk, is called bulk deformation. And I want you to, let me get this Zoom video out of the way. And I want you to focus on the definition. So we define bulk deformation as a process which we change the geometry by not removing material or adding materials. Remember, so far, the manufacturing process that we learn, we either add things or we remove things. So if you are adding things, let's say we are adding layer by layer to make something, we call it additive manufacturing. Very similar to my initial, but this is additive manufacturing. So, and which is the topic of our next lecture, and is in fact is an exciting topic because we're going to move away from the traditional manufacturing processes. And if you're removing material, making things by removing material, it is in a category of machining. I keep writing machining, spell it right. Wrong. So Bulk deformation is neither of these. We are not removing anything and we are not adding anything. So we change the geometry to get to the desired shape by plastic deformation of the bulk material. That's the definition. So our original material can have any form, but the most common are either using like a square cross section or using a circular cross section. So that's for the original material, or maybe just a rectangular cross section. And not very important, but just the terminology. If the cross section of the original bulk material that we use is either a square or circular, we usually call it a billet. And if it is in a form of like a rectangular cross section, then people use the term slab. But again, as I said, people use these terminologies interchangeably, and that's totally fine. But if you heard, so the billet is the very common name for the original bulk material to start making things. So this process can be cold and can be hot. And we discussed about the cold process and hot process before. And we even joke about it that you like it hot or cold. But the bulk deformation can be cold, meaning that no initial heat involved, or it can be hot, where we basically we increase the temperature, the bulk material, but we don't melt it. We get to maybe 60 or 70% of the melting temperature to make it more malleable, to make it more softer and make it easier to deform. In general, we say cold operation is good for small parts, or let's say a small change in shape. So if you are making few millimeters or maybe few centimeters, depends on the original size, maybe cold process is the way to go. And soon we will quantify these, and we tell you exactly, and I will tell you exactly what do we mean by small change and big change. So, but typically if it's a large deformation, then we prefer to use hot operation, which, as I said again, in a moment, I will explain these in more details. So bulk deformation, there are four main categories, which is the focus are the topics for our today lecture. So rolling, drawing, extrusion, and forging. As the name implies, so in rolling, it involves rollers to change the shape that we want. So you can think of, if you haven't watched those YouTube videos that you post, I posted, I hope you watch it. But if you haven't watched, rolling involves two rollers, which they squeeze a slab of material between two rollers to reduce the cross section or change the cross section. Drawing and extrusion, similar concept. In drawing, we pull out a material out of a profile to get a cross section that we want. Extrusion, we push a material into a profile. And forging is more like hammering. If you watch this TV show, Forge and Fire, where they make knives by hammering and a slow, gradual deformation of a hot piece of metal, then that's the forging. But we're going to talk about the industrial, basically, level of forging, not making knives. So let's look at the benefit of forging. Why forging is popular in making some parts. Let me, for a moment, I switch to my document camera. Let's get rid of these aluminum extrusion. And this is a dumbbell that is only 3 pounds. So maybe you laugh. It's not the weight that I work out with. But anyway, so I picked this one because it fit on my table. So a 3 pounds dumbbell. Let's say I want to make these things. So unlike the previous example that I showed you, this one can be made by casting, right? Or we can use machining to make this. Casting these things is going to have one issue. And typically in casting, we said we are not happy if the thickness is big, and because then the solidification is going to take time. And time in manufacturing is a big factor because it's going to have basically increase the cost, and we are not happy about that. And you can imagine making such a things like a dumbbell, only a few dollars. You don't want to spend wait, let's say, for 10 or 15 minutes just to make one dumbbell. So casting is not maybe a good way. Let's focus now for maybe two processes, maybe machining to make this one. If I want to make this out of machining, so I have to start with the original, let's say, material, like this one. And then the other method that we're going to focus is going to be with forging. So original material like that. So we can see I need to remove material, and we can easily put this cylindrical shape on a lathe and remove material to make this dumbbell, right? So I remove this portion. So if I'm removing this portion, it means it is a waste. I have to throw them away, or of course we recycle them. So if I'm making a 3 pound dumbbell, so it means my initial material probably has to be 4 pounds, because we are now getting rid of 1 pound here. All right. So, but if I'm making, let's say, this dumbbell by forging, and typically I hammer the needle or compress the needle, then you see there is no waste of material. And my original things, if it is 3 pound, this one also is 3 pound. So no waste, basically. All right. That's one benefit of forging. But another important feature is, let's say that our original cylinder that we started by, the grain, let's say, has a uniform grain of like longitudinal grain like that. These are the grain. And if you recall, at the very, very beginning, we discussed about the grain and grain orientation. Let's ideally think that this is the original material has these nice, clean grains parallel to the longitudinal direction. So if I make like this dumbbell by machining, so my grain are gonna stay in the same parallel way. So this is the grain basically. While if I make it by forging, then the grain has to go in more like a, we can say like ideally, in a contour shape like that. So this is gonna be the orientation of the grains. It looks like a bone rather than a dumbbell, but accept my drawing. So my point here is, if you look at the grain direction for this one, they are parallel, but the second one by forging, the grain has been entangled to each other. And it can be shown both experimentally, like doing tests, and also by simulation, which is not the topic of this course, that if we have a grain orientation like that, which like a contour shape, then we are going to get a stronger part. And by the way, guys, like always, when you have a question, please unmute yourself and ask question. I guess somebody had a question.
Yeah, I was just wondering, what did you mean by grain over there? Because I thought grains were just like small portions, like a microscopic portion that's oriented in a different way from its neighboring portion.
Exactly, that's a good question. So it is here what we mean by grain is more like the grain orientation or the line that grains have been, let's say, settled. If you can think of, I believe I showed you at the very, very beginning, and in a moment I have like a more maybe illustration that can make more sense. It's more like the orientation of the grain, all right? Wait for a couple of slides later, which you will see an illustration of the grain orientation. What do I mean by that? All right?
Yep.
So, and other factors that we can mention for forging is there is a high production rate. The process usually is automated, it's fast. Unlike casting, we don't need to wait for solidification. You saw the reason or the logic why we save material. And of course, the grain orientation, which this example of dumbbell sort of give you an idea, but we will discuss it and I will elaborate more. So as Ahmad asked, so we'll talk about it later in few slides later. And this make this process sort of a favorable process for making many things. So with this introduction, this is the objective of this module. So in this module, I expect you to learn the principle. Again, let me get rid of this video, Zoom video. So I expect you guys to learn the basic, and the machinery involves for rolling, extrusion, drawing, and forging, the 4 categories of bulk deformation. And like always, we will apply a little bit of our knowledge in engineering, basically the courses that we have learned before, to estimate the requirement, which here you can guess the requirement is the force. How much force do I need to deform the material to get to the desired shape that we want? This is our objective for this module. And this is basically the outline of or the sequence of this module. We'll start with rolling. And rolling, particularly, we can talk about plate rolling. You can guess from the name, and hopefully if you watch the videos, these things make sense. Thread rolling for making threads, and ring rolling just to make rings, such as the rings for ball bearing or larger rings. Extrusion and drawing, very similar, except the concept of pushing a material or pulling a material. And then forging, which has 3 ways of doing forging: open die, closed die, and flashless forging, which we'll get to that hopefully. So as you can see, it's today's topic is a little bit hectic, but it's super simple, and you will see. And I'm gonna maybe go with a faster pace, but please feel free to ask questions at any point. Just as I said before, I'm not going to check the chat. If you have question, interrupt me, unmute yourself and interrupt me. Let's start with rolling. So rolling definition is very simple. We have 2 rolls, and as you can see in this image, we squeeze basically a slab of metal between these 2 rollers, and we reduce basically the thickness of these things. That's the process, nothing complicated about it. And I put a video link here, which you can watch the details, but just a portion of that video here. So with maybe a nice music, makes you happier if you are especially tired. So we have the billet, and it seems to be a hot roll, and it's squeezed between these 2 basically rollers. And another example.
Steel is squeezed between.
So let me start. So we don't have to have just 2 flat rollers. It can be any shape, even from the side, to get the cross section that we want, like this one.
Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of thousands of tons. The rolls, therefore, run in massive bearings, mounted in housings of enormous strength and driven by powerful electric motors.
Well, please watch the entire video. It's short, it's just 9 or 10 minutes, and there are more details which explain there, which is going to benefit you guys learning about it. So coming back to this grain idea that Ahmad asked, you see here the grain, the orientation is just more like, we can say, random, but when we go through these two rolls, then they are going to be, ideally, we can say they are going to be aligned in a line and like that, more like longitudinal, let's say, grain direction. And in that way, there is a larger area, and grain, it can provide a higher strength. Again, if you recall, in lecture 1 or 2, we talk about grain size and grain orientation, how it can affect the strength of a material, right? And there is another video which in detail it explained, but let me play just a portion of it. Just in fact, this first part that you just saw. Here you can see in this animation the grain. Sort of, okay, want to play it again. So, but again, watch this video, please. And it shows like nicely why when we have this elongated grain, we are going to get a strength, higher strength for the final part. And I put the links over there again for you guys. Sometimes we have to do multiple steps for rolling. Let's say I want to get from the original thickness, let's call the original thickness T, or maybe T0. So this is T0. And let's say I wish to get to the final thickness of, and here T final. But there is a limitation to do so. We cannot always do it in one shot. And there is basically a simple empirical formula which says, let's call delta T the difference between T0 and T final. And the delta T max, like the maximum that we can basically squeeze and reduce the thickness, has this form, mu squared multiplied by R. And again, this is an empirical formula. In your textbook, it briefly explains and partially prove it. But in most of engineering book, we just use this formula. That's the maximum we can reduce the thickness. And in this formula, R is the radius of the basically the roller. So let me find this. This is R. And mu is the friction between the roller and the plate, which is not an easy job to find mu. Again, as a general rule of thumb, if it is a cold rolling, you can use the value of mu 0.1. It's just for the initial estimation. If it's a hot rolling, then use the value of 0.4. But if the material that you want to roll and the value of friction and based on the machine that you're using is available for mu, you can use basically the actual friction. However, this process involves at the very beginning when they set up the machine involves lots of trial and error, and they start with this rough estimation at the beginning to make sure how many steps they need. And you can see from this formula, the bigger the roller size, of course, you can decrease or reduce the thickness higher. However, you need more power, which when we get to engineering analysis, we can calculate the power that we need for this machine. And this power, you can guess, it's not just a function of how much we reduce it, it's also the function of how fast we want this plate to move, or how fast is our production, which we will get to that. All right. Is there any question, guys, so far? Quiet, seems to be good. Let's move to another, let's say, subtopic of rolling, which is thread rolling. Thread rolling, basically every screws and every bolts and nuts that you see out there, like the cheap one, not the fancy, expensive one, which are made by machining or CNC process, are made by basically rolling. And this is the most common way to make basically screws. I have a short demo of this one. It was very short. One more time. 2 rollers. We have the patterns. We squeeze the cylinder between these two. And you've seen we use oil, constantly oil, to create the thread that we want. There are varieties of the machine that you can use, and there is no particular difference in the final product. It's just a difference between the die. So the die, it can be like here we have the stationary die and moving die. It can be just flat plates. The picture in the middle shows a similar concept that you just saw in the video. And then the last one, as you can see here, has the stationary die. And then we have the inner rotating die, basically. There is, again, as I said, no difference between the final product. It's just a different machine, different setup, and how they produce these parts. And with the similar concept that I explained for that basically dumbbell, the idea of the grain orientation, if you think of the original grain for the raw material that we have, let's say a cylinder, and now you machine it, so the orientation is going to stay the same, basically, for the grains, or the grains are going to stay the same, if you can think of that way. And now when you squeeze them to get to the shape that you want, here the thread, the grain are going to form somehow to the shape that we want, and they entangle to each other. So I'm not sure, Ahmad, by now, if the question you ask is now you got a better idea. You can imagine, like here in this case, that you have the grain, let's say I just exaggerate it. Let's say you have the grain oriented like that. Let's say this is your grain for the part that you want. And what all you did here, you just remove the extra material to get the shape that you want. But here you force the grain sort of to conform maybe to the shape that you want. It's very difficult to draw. Let's say this is the same things, but here your grain are gonna be maybe form in this shape and follow the contour of the shape that you have here, like as we show it over here. You see the grains, like they're their flow or their orientation is just follow the shape or the contour, the outer contour of the part that we want, like similar to that dumbbell example. And another subtopic of rolling is ring rolling. And ring rolling, again, very common. Without ring rolling, making the basically the railroad tires, like here, steel railroads tire, is almost impossible because we want a very strong tires, steel tires for a train. And also we want a lot of them, so we don't want the process to be super expensive. We can make them by machining process, let's say with the CNC process. However, the process then after that requires a lot of hardening to get the surface hardening, and maybe we don't get the desired strength that we wish to have. So the ring rolling, I guess again, I posted a video which you were supposed to watch before, but the whole idea is we have the main roll here as I showed in this schematic. We have the mandrel, and which we squeeze the ring between the inner cylinder or inner roll and outer roll, the main roll and the mandrel. We squeeze the ring between these two, and you see we have these two axial roll, or sometimes we call them edge roll, which they are in a form of like they have a more like a cone shape, and their task is to first control the formation in vertical direction, and also they try to draw the ring out and make the ring larger and bigger. Please watch that video later. And here I guess I have another short video, if I can play it.
Against gas and liquids. The optimized grain flow ensures excellent tensile strength. Furthermore, the surface is clean and smooth. Perfectly round and full-edged, these rings feature a minimal machining allowance. This makes them ideal for CNC machining without any rough turning being necessary beforehand. Depending on what they are required.
Yeah, I just showed a portion of that video. Please watch the whole thing. And
against gas and liquids.
And somewhere
the
here,
optimized grain flow ensures excellent tensile strength. Further,
you see here the whole process is under control. We have like here, which they probably automated how much force, how fast these axial ring, they can pull the things out and how much force you need. Of course, it depends on what you're making and the size of the ring that you're making. Again, I'll encourage you to watch the whole things. The link is there. All right. So, and depends, you can guess, on the roll that we use, we can get different profile, right? If the inner roll is just a simple cylinder, we get a simple ring. But if the inner ring has, let's say, a pattern on it, or the outer roll, the same idea, we can get the shape that we want, similar to this profile that you'll see in this example, which the roll bearing is a good example that we want this hollow shape inside. Let's move on to extrusion. So for rolling, then you learn the idea. We have two rollers or multiple rollers. We squeeze a slab or a material between roller to get the desired cross section that we want. Extrusion, you can think of it as basically the same idea. We have the original material, but this time we push it into a profile. Let's say if I want to make a cross section, aluminum cross extrusion with this cross section, then you can this cross section, and then we need to create a profile with a negative of these, let's say, cross section. Then you can think of more like old toys, which kids play with this clay, squeeze it into a profile and get different shapes. I'm not sure if it was are available now, but it was maybe for our generation, which we had such a toy with clay and dough, which we could squeeze it to a profile to get different shape. I believe you watched a video which I posted how these aluminum extrusion are made, but here a quick demo. So in this schematic or this cartoon, you'll see we have the billet going there and we push it to a profile. And here the profile is very simple. It's just simple cross section. And obviously at the end, we need to trim the excessive material. And we get the basically the cross section that we want. All right, it is about extrusion, which is a very simple concept again. Drawing, the idea is basically the same. For some reason, today my video is going back and forth. So drawing, the same idea, but instead of pushing it, you now draw it out of the profile that you want. It's very common for making tubes, or let's say you have a tube, you want to reduce the thickness or the diameter of the tube. Let me see. Yeah, here in this video it shows the whole process to make steel tubes. But also I have here a shorter video. If I can, which is basically a portion of that link that I posted there.
Is there any reason that we can't simultaneously draw and extrude?
So Jesse, say it again.
Is there any reason we can't do both at the same time, and possibly combine their advantages?
For drawing, you mean?
So simultaneously draw and extrude the billet.
Usually we have to do that, and the main reason is we just draw it, like the material, maybe it stress past the yielding point and it tear down. However, when we do the drawing, we prefer to do the drawing, let's say in this demo as it shows. So you're saying that why don't we do it simultaneously? Like at the same time that we, let's say, draw this tube, we don't push it. This is, I believe, what you're asking, right?
Yeah, I'm wondering, like, can we push and pull at the same time?
So it might be for some particular application, but again, not very common because we don't want to apply too much stress at the same time that we are drawing it out, like in this example. We don't want to push it because then we mess up with the grain and grain orientation and the final shape that we want. Drawing, okay, very common for making tubes, like as shows in this video. Or later you will watch this, if you haven't, this steel tube production. And finally, let's get to forging. Let's see what we'll do in terms of time. Maybe I have to go a little bit over time today, but again, since the meeting is being recorded, that's fine. If you have other lecture or you have to go, that's fine. Let's see where we get, all right? So forging, as I said at the beginning, one of the very popular manufacturing process or bulk deformation. It's we like this process because of the final strength that we get out of it. It's in our favor, not too much waste. You've seen before, I intentionally put these examples like crankshaft. It was an example which we discussed last lecture that we can make it by powder metallurgy. Or gears, you remember gears? We said you can make it by CNC machining. However, it takes time and it wastes a lot of material. Then we learned that the best manufacturing to make gears is by powder metallurgy. And today we'll see also we can make it by forging. And you can discuss the pros and cons of making gears by powder metallurgy and by forging, but simply we'll say if it's a small gear and we don't want like super strong, maybe we'll go with powder metallurgy. And if it is a larger one, we go with forging. And another factor is the original material that we want to make the gear out of. Is it easy to make it out of powder or make powder out of that material? Or maybe, again, let's focus on the example of making gear. Nobody make gear out of tungsten, but just for the sake of discussion, tungsten, you saw powder metallurgy is very common because melting it is difficult. We prefer to work with powder to make tools, tungsten tools. Let's say you want to make gear. So between forging and powder metallurgy, if the material is tungsten, then most likely you go with powder because you need a lot of force to forge original material to make gears. And other example, like in structural parts or in jet engine turbines, maybe there are some parts that we need high strength, and forging is something that will go. So forging, we will do forging either by hammering, like as I said, like here, first line, like impact or gradual force. Impact, more like again in that TV show when they make knives, or in the 1,000 years ago, 2,000 years ago, when they made knives or sword or other tools, they use hammering, or it can be a gradual, basically load. Depends on what we do. The machinery is either forging hammer or it's a forging press, and just terminology for machining that we will use. And forging operation, three main categories: open die. So the mold or the die that we have is open. It's not basically a container. Impression die. So we create an impression. We create an impressed of the original. So it's a closed die, we can say. And then flashless, which I'll get to that and make sense why we call it flashless. You can watch that video later. If you haven't, one of those links before.
Impression die forging accounts for the vast majority of all commercial forging production. Impression die forging accounts for the vast majority of all commercial forging production. The name comes from the specially fabricated impressions in the matched dies themselves. Although open die forging takes the honors when it comes to maximum customization, impression die results are within closer dimensional tolerances. They can also range from a few ounces to over 10,000 pounds, and from a fraction of an inch to over 26 feet. And if other processes are added at various production stages, the quality and production economy of the end result is further enhanced.
And again, please watch some of those videos later. It's an interesting process. I had the luxury to work in a company which made parts for cars, and that company made a knuckle steer, like portion of a car before the tires, basically. It's a large part, and the part is usually made by forging. And seeing like a big, gigantic piece of steel, and it goes under a big press and being forged, it's really impressive how you can form a metal to get to the desired shape that you want. So let's briefly review these three types. Open die, also known as upset forging, different again terminology people use. As you can see, there is in fact no die. It's you just compress either by gradual force a part between two, maybe a slab, or two die, which is just two flat die, to change the shape and form of it. Like as I showed in this schematic, from H0 and first diameter, like D0, you get to the D final and H final. either you go gradually, first it is under one press, and you get to H, and then the next step, and sometimes you have to do several steps. Depends on the process, like as you see in this picture A, you can just reduce the thickness of a portion of a part. You can rotate it in picture like B to get a round basically shape, or maybe like this ring, which you can apply the load, normally hammering it, and while you're rotating the ring to forge it to the shape that you want. Usually these one are not automated, and for just maybe quick, simple process, if you're just making one or few parts, people use it. Very similar to that video that you saw for the grain orientation, basically. Forging also gives us a favorable grain orientation and make the final part strength, which is again the repeat of what we just discussed related for rolling. So I'm not going to go through that. Let's look at impression die forging, which is also known as closed die forging. Unlike the open die, this time we have basically two halves of the mold, and we impress basically the original material to the shape that we want. And as you can see here, let's say after we squeeze this material between these two halves, here we are creating like a little flash, and this flash can have and play an important role here, or has an important function for us. So the flash, you can see here, it start to form, and here the final parts, we have the flash, which later we need to basically maybe use machining process or other process to remove this flash. So what do you think can be the main function of these flash? I said this flash can have an important function, but what do you think can be that function?
It cools first and provides pressure.
Provides pressure. Thank you, Kutan. So Kutan is saying, which is true, it provides inside pressure. So as Kutan pointed out, the way it works is you can see on these images, maybe provide a better illustration. So when the flash forms, it contains the whole material inside basically the molds, and it creates fundamentally more pressure, and so we can make sure that we are feeling like the intricate details of the part, right? So let me see if there is any questions so far. And sorry guys, today we were a little bit faster than normal because, as I said at the beginning, this topic is easy. However, there are lots of things, lots of subtopics in this topic. All right, so I'm gonna go maybe, again, 10 minutes over time or maybe longer, but you're welcome if you want to leave, because the recorded lecture will be available. But let's finish the few more slides that we have. So, and then the last type of forging is flashless forging, which is also known as precision forging, or some people, they call it a real or true close die forging. And why is that? Because if we go back one step here, although it is, people call this one closed die, see closed die forging, it's not 100% close, and that's because of this flash. So we'll get here, you see on these picture E here. So because of the flash, it's not 100% closed. But again, it's just a terminology. If you saw somewhere people call it a real or true closed die forging, they are referring to precision forging or flashless forging. It is flashless because unlike the previous one, there is no flash. It's good for simple and small parts because you can imagine it requires a lot of force. So like if I'm gonna get maybe a simple cylinder or simple part, and good application for this type is one is coin making. The very first example that we discussed that it's difficult to make it by other methods, which is this process, people call it coining. And another example, which you were supposed to watch, is how these ball bearings are made, basically, which is a little bit longer videos. However, I encourage you to watch. There are a lot of learnings in that as well. So we are getting to the engineering analysis of forging. Let me see if, I guess we'd better finish it because then you can basically work on assignment 4, which is basically the last assignment. And it's just 2 questions. And this one is super simple. Let's quickly get to that. So as I said at the beginning, we want to apply our basically like our basic engineering knowledge to calculate how much force we need, let's say in forging. So let's say I'm applying a force F, and of course equal force at the bottom F, but usually the bottom is fixed. And the question is, how much force do I need to get from H0 to, I get from this one to H1. So this is the question we want to answer. We want to get from H0 to H1. Why? I'm not sure it's doing that. Okay. We want to get from H0 to H1. And the question is how much force we need. And then of course, how much force we need to get from H1 to H2, or maybe several other steps. Okay. So we can simply say, well, force that I need is going to be equal to stress sigma multiplied by epsilon. Can I say that? Or sorry, sigma multiplied by area. And here we just say A0. This is the amount of force that I need to get to deform it. And sigma is stress. So here is the stress. And this is basically a simple definition of a stress that you had before. You learned it in Mech 2. And that simply sigma is F over A, right? So things can get a little bit complicated here because now we are not dealing with a very simple like bar under compression. And people have done some study and they add another things here. They call it KF. And KF, something people call it shape factor. So this is shape factor. So what it means is people try to apply this formula and test it with the actual load, and empirically they found that they cannot use this simple straightforward formula, and depends on the shape and the geometry they want to form, there is a factor which they need to add. And after many maybe trial and error, they found that this KF, these numbers can give you a good estimation of the forces that you need. So let's start with the simple one. If it's a flashless die, then simply, if you're doing coining, number 6 is your magic number. And if you're doing a complex shape, then 8 is the number. And these numbers are very common in most of engineering textbook. And if you're doing impression die, then if it's a simple shape, simple geometry, 6, and then 8, and then a very complex 10. You may say, well, how do I know the shape that I'm making is complex or simple, right? And this is where in manufacturing, the experience come to play. The people who have used the machine many times, they have done lots of experiment and made a lot of parts with it, and they fail and they realize maybe they have to adjust the force. So many of these numbers is for the very, very beginning when we just want to do a rough estimation. So we know for this shape, what should we have for the, let's say, for the hydraulic, if we are doing it by pressing for forging. And if it's an open die, then there is another empirical formula, which the D0 and H0, the original shape, and the friction, here mu is the friction between the die and with the actual part. So that part, like finding KF, it's easy, and we can sort of use a number like the shape factor. The complexity comes here when we need to find out like the sigma, like a stress. How do we know how much is the sigma? Well, in the old day when you had Mech 2 and then later you learned Mech 360, sigma for you guys was very easy. You say sigma is equal to epsilon multiplied by E, and it has a name. You remember the name? What was the rule?
Hooke's law?
Hooke law, exactly. So that was the Hooke law. We have the epsilon and we have the material E modulo of elasticity, good to go. And you know the definition for epsilon, right? Epsilon, you say, well, the formation divided by initial basically length, which is H1 minus H0 divided by H0. So good to go. We have the sigma. Unfortunately, life is not that simple, and none of these formula works here. And you can guess why. Any idea why this formula is no longer valid here?
The deformation is not
Stress
linear.
concentration?
So maybe one by one. Jesse, you want to go first?
I was going to say stress concentrations.
Stress concentration, but here we don't have any stress concentration. Or maybe we do, however, we can say that this is between two flat slabs, right? They are uniformly compressed.
Yeah, I was just gonna say it's in the plastic zone, so it's not really linear relationship.
Good point. That's right, Ahmad. We are getting to the plastic deformation. So these are not valid, and we need to find another way to calculate this sigma, and this is what we are going to discuss. We need to introduce two parameters. One is strength coefficient and one is strain hardening. And let me quickly get to those, and these are very, very simple. So let's first look back at the basically the simple idea of Hooke law and those nice graphs that we learned, like stress and strain. And we learned that there is this linear portion, and after that linear portion, we have this plastic deformation. And as we said, we have this slope here, which from this slope, if let's say this is alpha, then tangent of alpha, we call it modulo of elasticity, and everybody was happy because we have this formula sigma epsilon multiplied by E, and epsilon, as I said, deformation, initial length. And we simply define sigma as F divided by A. And we, if you recall, we said we get these basically graph usually by doing experiment, and we have this specimen, thread at the top, thread at the bottom. Oh, if we accept it as thread, it is under tension in a tensile test. However, the big flaw with this formula, even for the elastic region, is this A is not constant, right? As we basically stretch this part, this is not going to be constant. Oh, for some reason, my pen doesn't work properly today. So not constant. So, and secondly, this L0 also is not constant. So L0 is at the beginning, but it's gonna become bigger and bigger. So none of these are valid if we use true strain and true stress. So in other words, if I draw the actual plot, but true values. So it's funny when we say true stress and true strain, it means the previous one, which we told you was a lie, right? So this is, let's call it true stress. So this is true sigma, and this is true epsilon, basically. So true epsilon, we can define it. I'm just writing down here. Epsilon true, it can be defined as delta L divided by L, and then we integral from L0 to whatever L we get. So we're going to get to the logarithm of L over L0, right? This is what we know as true epsilon. And for sigma, this is not going to be valid, the Hooke law here. And again, I'm not going to go to the details of it. That there is a course, I believe, MEC 460, which discuss and go to depth of these, which is not the focus of this course. Basically, in this course, we focus on manufacturing mainly. So the Hooke law now becomes, get a form like now becomes a constant K multiplied by epsilon, but true epsilon. And this is true n to power of n. So our original Hooke law turned to this guy. K is a constant, and this is what we call it strain coefficient, and m, it's something people call it strain hardening exponent. So if I plot this graph now, sigma true, epsilon true, I will get something more like this one if I try to draw it, something like that. All right. And what is K, what is N in this graph? If we draw at the very beginning like a tangent line, the slope of this tangent line is equal to n. And what else? If I find a point when epsilon is 1, wherever it is, just randomly put some point here, epsilon is equal to 1, truest strain. And then if I continue this line to intersect that things, can I move my video? I hope so. I should have think of my drawing better ahead of time. So I know it's getting messy here, but this is just for your own understanding where this K and basically N are coming from. So here now they intersect, and this is where people call it K value. Okay. Luckily, we don't need to know these graphs and these complicated formula. there are engineering tables which they made these K and N available. And this is what we were waiting for. If I go one step here, right here. So for different materials, you can look up these things, strength, K, for example, for steel, for aluminum, and this N exponent, right? Strain hardening and exponent. So you don't need to know all these details, but this was just to give you an idea where these things are coming from. Now with this knowledge, let's complete our formula. So the force that we need, we said it's equal to, at the beginning, sigma multiplied by A0, right? And then we said we need to have a coefficient here, Kf, for the final shape, for the shape factor. And then the sigma, we found a formula for it, which is K multiplied by epsilon power of N A0. So it depends on the material that you have. Now you can estimate the force that you need for forging. All right. So looks complicated like these graphs. However, this formula, using this formula is super easy. You want to estimate the force. You have Kf as a constant. Depends on your material. You have K and you have N. A0, the original area cross section. Then you need epsilon. So what is epsilon?
So delta over L naught.
Delta, okay, let me move back to this guy here. Remember, we are calculating the force to get from H0 to H1, and we said this is wrong, right? And this is A0. And guys, don't forget, this is a force that we want to get from here to there. And then later you need to use the formula, how much force you need to get from the middle one to C. So here, can we say epsilon is equal to logarithm of H1 divided by H0, right? Remember the definition for true strain is logarithm of L over L0. So epsilon here is going to be ln H1 divided by H0. All right? And that's it. It's the amount of force we need for forging. K and N, we have them in tables. Keep in mind, N is a small number, usually between 0 and 0.5. This is the range here, 0.2 and 0.4, as you can see. And you can find them for different material. And now you learn where they come from. And this is my last slide. And I know it's getting late, but it's just one formula we need. As I said at the beginning, how much force we need or how much power we need for rolling. So let me just write down the formula and later maybe I'll explain it more, but just to complete our notes here, the power that we need for each motor here that we are rotating. So for each roller, let's say, one at the top, one at the bottom. The power that we need is equal to the torque that we need multiplied by omega, the rotation speed, right? How fast this thing is rotating. So, and let's say this thing is rotating with N, usually in RPM. That's the common basically unit we use for motors. So it's going to be then torque multiplied by 2 pi N divided by 60, right? Make RPM to radian per second. So T, the torque that we need, again, this formula, there are some proof, there are some papers if you are interested to look them up, and combined with some empirical, basically data, it gets a form of R multiplied by T0 minus TF, and then multiplied by the width, or width 0. Here is the width that we are talking about. Original width, and then multiply everything. Here is where it gets ugly. Multiply it by K epsilon to power of N, which now looks familiar, right? K is the strength coefficient, epsilon is the true strain, and N is the strain hardening, divided by 1 plus N. Okay, so the whole things, let me move it there so you don't get confused. So if I move the whole things a little bit there, I made some room, get rid of that. Now we can move the whole things up there. All right, so this is basically the formula for power. Please go through it, and if, oh, forgot here something important. So equal to 2 pi n divided by 60. So R is the radius of the roller, N is the rotation speed, and T0 and TF we are getting from here. They call it H0. Let's be consistent with this shape. I know I call it T. Let's call them H0 to H final. And some things that I've seen most of the students, when they solve this problem, they make mistake is finding epsilon. Epsilon, remember, is the true strain. And here in this case, it's go back to that idea of definition for true strain is HF divided by H0. Assignment 4 that you will do one question for rolling, which you will see how you can use this formula. And maybe later I will provide more explanation, but this is the whole concept for this formula. I see it's getting very late, and sorry guys, it was a long lecture. Thanks for those who stayed. And right, we're done almost. And if you guys have questions, I'm happy to answer. If not, please study this topic. I know there were a lot of details. Please watch the YouTube videos, and then maybe next lecture, if you have a question, I will provide more explanation for you guys. All right? So is there any question, or it's too late? We should say goodbye.
Can you go back 2 slides, please?
2 slides? Absolutely. Like this one? This is what you wanted to do?
Yeah, thank you.
All right. And I'll post these notes. So these notes by tonight, both the video and the basically the notes will be posted. Okay. So let me stop recording here. Stop sharing. And somewhere I should be able to start recording.